Good morning, everyone. I will just start very soon. Okay. So good morning. Before we start, let me just tell you that there is some noise coming from my side. There is some kind of a repair work going on in one of the apartments above. So that is going to be a kind of a nuisance parameter. So one has to we have to bear with it. So we were looking at two examples in the last class. The first one we had sort of finished. We will revisit that first example again later. The second example, we had shown that the pi given by this is a stationary distribution. And of course, it's also uniqueness also we had shown. So basically it is the unique stationary distribution. But in addition to that, today we will show directly that that distribution is a limiting probability distribution for X. And that together with the theorem we had proved earlier would sort of again imply that pi given by the dagger is the unique stationary distribution. This is the last slide of last class. Okay. Remember this, keep in mind this matrix, the transition probability matrix of this model. Yeah. If you have not noted it down, please note it down. Since pi p, that is the defining equation for stationarity, that involves considering pi as a kind of row vector and this is a matrix. So in that multiplication, we will be for corresponding to the column, this thing corresponding to 0, we will be going down like this and down like this. So that will sort of make it clear many expressions that we have written and also we will be writing today. Yeah. Now for any n greater than or equal to 1 and any state in the state space, if you consider p super n I0, say we have to consider limit as n going to infinity of this, and the limit should be independent of I, and that should depend only on 0. And so in this case, note that this is nothing but this index L going from 0 to infinity, p super n minus 1 subscript IL p L0. This is that matrix multiplication from the left. So this guy PL0 is 0 for, is equal to 1 minus P for every L. The first column in the matrix P. That is a constant 1 minus P throughout. So therefore, that comes out of the summation. And what you are left with is just summation over this. But we know that P super n minus 1 is a stochastic matrix, even when the state space is not finite. Say there you are fixing the row I and here summing over L. So therefore, this guy is equal to, the summation is equal to 1. So consequently, P super n I0 is 1 minus P for every I and every n. So consequently, limit as n goes to infinity of this would also be 1 minus P, and the limit is independent of I. Please note it. Okay. Now, before we go to the next slide, so we will try to do similar things for P super Nij for various j. Then that limit should depend on j, not on I. So the approach we will take is, since that would concern the limiting behavior, we can even consider n greater than or equal to some particular k. Okay, so we will be dealing with n greater than or equal to j plus 1. Okay, as you will see. So let j be greater than or equal to 1 and n greater than or equal to j plus 1. So if j is fixed, this n also will be fixed. Or rather not fixed, it will be some number greater than or equal to j plus 1. For all numbers n greater than or equal to j plus 1, we will show something like what we have seen, that for all n greater than j plus 1, this guy would be a constant. Okay. So when j is greater than or equal to 1, for any I in the state space, note that PLJ equal to 0 for L not equal to j minus 1. So one can go back to that matrix and see that. Yeah. So in this column, for example, this is the only non-zero. And that corresponds to, this is, what is it, 0, 1, 2, 3. So this is the 0, 1, 2, 3. Yeah, this is the entry corresponding to second row. Not second row, the row corresponding to I equal to 2. Yeah, only this is non-zero. Yeah, that's what. So PLJ is equal to 0 for any L not equal to j minus 1. Now, if you put n greater than or equal to j plus 1, n minus j is greater than or equal to 1. And we have already shown that P super k in the previous slide. P super k I0 is 1 minus P for every k greater than or equal to 1. Consequently, we get P super n ij, so which is summation L going from 0 to infinity of this P super n minus 1 subscript IL PLJ. So in this, only the term corresponding to L equal to j minus 1 survives. So therefore, this is equal to P sub j minus 1 comma j P super n minus 1 I j minus 1. But we know this is equal to little p. So this is p times P super n minus 1 I j minus 1. But by the same argument, we would get that P super n minus 1 I j minus 1 would be P multiplied with P super n minus 2 I j minus 2. So therefore, this becomes P square times that. So that way you can go up to n minus j. And then that in the process you get here, this thing becomes 0, and that we already know. So therefore, P super n ij is 1 minus P times P super j, I mean P power j. So we have this P super n ij equal to 1 minus time P power j for all n greater than or equal to j plus 1. Please note it down if you want. So thus we have for any k greater than or equal to 0 and I greater than or equal to 0, P super n ik is equal to 1 minus.
Sir, actually your voice is quite low. Can you just...
There is also some noise coming from elsewhere. So
now it is fine. Now it is fine.
Okay.
Now it is okay. Fine.
That means I should not lean back on my chair. Okay, good. Yeah, that's a minor sacrifice. Yeah, now is it okay? Am I audible? Okay.
Yeah, it's perfectly all right. Yeah. Perfectly all right. Yeah.
So we have got for every k greater than or equal to 0 and I greater than or equal to 0, P super n sub ik is 1 minus P times P to the power k, which precisely is our pi k for all n greater than or equal to k plus 1. The preceding slide, what I had written as j, I am writing it as k. Consequently, limit of this quantity as n goes to infinity is also this. And that limit is independent of I. So it follows limit n going to infinity, P super n sub ik is pi k for every k and every I in the state space. And of course, that limit is independent of I. Independent of I for any k. So pi is a limiting probability distribution, and therefore it is also the unique stationary probability distribution for the Markov chain Xm. So in this example 2, the stationary distribution also turns out to be the limiting distribution. And the earlier example, we had a stationary distribution, which we proved it was unique also, but that was not a limiting distribution. And also, as some of you also pointed out, the difference between the two cases is what we had observed. Yeah, P squared. Okay, P. Let us take a look at P. Yeah. In this case, note that you can return to any state only in even number of steps. For example, if you start from, so this is the state space is 1, 2, 3, starts from, if you start from 1, you can come back to 1 only at steps 2, 4, 6, things like that. You cannot come back in an odd number of steps. So there is certain amount of periodicity involved. This is a periodic. Whereas, and because of periodicity, we also saw that the p squared, all the diagonal entries are strictly positive, whereas in p, it was 0. And also, we also know from your probably one of the problem sheet questions that p to the power n is p if n is odd, and it is p squared if n is even. So there cannot be any limiting distribution. Whereas in this case, say for example, from 0, this is corresponds to 0. From state 0 to 0, you can come in even number of steps or some odd number of steps and so on. So it is aperiodic, which is sort of that is the case. We will define period in a very rigorous fashion later. Okay. So that sort of will be determine this stationary distribution being a limiting probability distribution. Yeah. I hope you have copied this down. Okay. Now we will define certain concepts. That is the average number of visits to a state. Okay. Let Xn be a Markov chain with state space S and transition probability matrix P. Let Y be a recurrent state for Xn. Say, for example, in the both examples that we considered, in the Markov chain is a recurrent Markov chain. And let T sub Y be the first hitting time of state Y. And this is the definition of Ty, which you had seen earlier. It is the main thing is this is infimum n greater than or equal to 1. N equal to 0 is excluded. If such a n exists, then it is that number. Otherwise, it is T sub Y is infinity. Ty equal to infinity means if it starts from Y, it never comes back to Y. Okay. And let us define M sub Y as expectation sub E sub Y Ty. That is expectation of Ty given that the initial point is Y. Note that Ty is a non-negative random variable. So this expectation can even be infinity. In the sense, it makes sense. You know, for a series consisting of only non-negative elements, the summation, if it diverges, one generally says that it is diverges to infinity. Whereas if it is something oscillating between plus and minus, you cannot say make such assertions. So this is the mean return time to state Y. That is the expected time of Ty. Expectation of Ty. This M sub Y will play a key role. Of course, we have defined this for recurrent states because recurrent states are going to place a kind of role, major role. Of course, this kind of definitions can be given for any state, even transient states. We will see what happens in that soon. Okay. So recall I sub y of z is 1 if z is equal to 1. I mean y, sorry. It is equal to 0 otherwise. This is the indicator function of the singleton set y. I. And now you define capital N sub little n of y is summation j going from 1 to n I sub y x j. So whenever xj is equal to y, this counts that. When xj is not equal to y, that particular j is not counted. So consequently, you see that capital N sub small n y is precisely the number of visits to state I during the first n time points. We have seen earlier a related thing without this subscript n, so that would be here going up to infinity. Naturally, of course, this n sub little n y as limit n goes to infinity will be that other one, n y. And as before, you can see that for a fixed y and n, this guy is a random variable taking values on non-negative integers and including possibly infinity. Please note it down. And also corresponding thing, since that there is an error here. There should be n capital N sub n. Yeah, please. That's a rather serious error I have made. Typo.
So sir, I have a question. So can you go to the previous slide, the definition of capital N sub n?
Yeah.
Okay.
So this is the random variable. We are
Okay.
taking the expectation of that in the next slide.
Okay. So we are studying expectation of n and y.
Yeah. So this should be expectation of n and y. So this n, it is missing. Little n is missing. Please. I will also make that correction in the notes. Little n.
Okay.
So note this is the GNXY with that correction would mean expected number of visits to state Y during the first n time points starting from little x. Please make that correction. If you are taking down notes now, please make that correction. So it is a simple exercise to show that this GNXY is precisely P super J XY. Because here the expectation of this random variable, this guy, is precisely the probability of reaching reaching y, sorry, the probability of reaching y in j steps starting from y.
So, sir, I have a question. So, if n is less than hitting time of y, t sub y, then
What?
expectation.
Sorry.
If the value of small n is less than hitting time of the state y starting from x, then can we say that the expectation of ex of n and y will be 0?
No, I don't understand. Yet
So basically,
this
so
this.
no. So what I'm saying, so can you go to the next slide where you define gn of xy?
Mhm.
Yeah. So if we fix x and y, we can view gn as function of n.
If fixed x and y, view function of little n. Yeah.
Little n. Now I am saying if this little n,
Uh-huh.
this little n is less than hitting time of y,
Little n is less than the little time of y, little hitting time of y. Hitting time
y,
of,
then gn of xy will be equal to 0.
yeah, the hitting time of, see, not that, but this is a random variable. For some other omega, it could be exceeding that. If you say that if it happens for all omega, then yes, you are right.
Yeah, yeah. I am saying it for all omega. Yeah.
Yeah.
Then right. Okay. Okay.
See, but many of these things will play a role only when n goes to little n goes to infinity, as you will see, because we are saying average number and so on. Yeah. Please make this correction. Okay. So this is exercise. This is a simple exercise. Similar thing we have done for the gxy, that where this n was not there, so it was going up to infinity. Actually, this g sub n xy will increase to gxy as n goes to infinity. So basically, yeah, you will see. Yeah, let me not make too many statements now. Okay, we have defined many of all these concepts now for recurrent state. But let us see what happens if y is transient. So if y is a transient state, then we know that p sub y, ty equal to infinity, that probability is strictly positive. That is, you might recall that transient means rho sub yy is strictly less than 1. Rho sub yy is precisely p sub y ty less than infinity. So if rho yy is strictly less than 1, probability of ty equal to infinity is positive. Consequently, this my, mean hitting time, mean value of the mean hitting time is infinite. So what it means is this t sub y is a random variable which can possibly take value infinity with positive probability. So the expectation of that is going to be infinity. So this is the first remark. Okay. So suppose y is a transient state. Then one theorem which we had proved, characterizing transient state and recurrent state. In that, use the parts which involve transient states, the second and third. And we have also observed this limit as n goes to infinity of capital N sub ny is precisely the ny which we had seen earlier. And this increasing limit, because naturally this denotes the number of visits to y during the first n time periods. This denotes the number of visits over the entire time horizon. So this, as n goes to infinity, will converge to increase to capital N sub y. And we have seen if y is a transient state, p sub x ny less than infinity is 1 for all x. I think that was that part A, second statement. And the third one was corresponding to gxy is a number. Gxy is finite for every x. So this is the total expected number of visits to y starting from x. Consequently, it follows that if you consider this guy, we noted that capital N sub n y is a random variable. That random variable you divide by n. So what this denotes is the average number of visits during the first n time points to y as a random variable, considered as a random variable. So that average, since this is going to be finite, so that average will also go to 0. So this is the kind of long-term time average concerning state y. And this is also an indicative of that in the expectation sense. I mean, I'm stating all these things to motivate the statement of a theorem, which we will see next class. Please note it down. Okay. The last remark concerning transient states. Y is a transient state. Suppose phi is a stationary probability measure for xn. So then by an exercise, that exercise 1, second part of that set, if the initial distribution is pi, we have seen the distribution of xn is pi for every n. So if the initial distribution is itself is the stationary probability distribution, then xn is equal to, xn is also pi. You have also seen it in the case of the Ehrenfest model. I think that was one of the exercises, one of the problems in problem set. So if the limiting distribution, that is the stationary distribution pi at a transient state happens to be positive, then by this result, it means probability xn equal to y is pi y, which is strictly positive for all n. Okay, so it's clear. I think this is fairly clear. Now let us go back to this. In second remark, we have seen that if y is a transient state, then this kind of average number of visits to state y, that average goes to 0 with probability 1. That is for almost every realization of that. I mean, this kind of statements, it is easier to explain and comprehend in terms of measure theory, but still just for almost every omega in the basic sample space, if you consider that thing, that kind of set will have probability 1. Those of you who are doing measure theoretic probability also, you can try to, like Aniruddhan, for example, you trust to write it in terms of measure theoretic terms. Okay, so now in view of these observations, these remarks we have found here, this seems to be extremely unlikely. That is, if there is stationary probability distribution exists, pi, that will give 0 mass to that transient states y. So at this stage, it seems very unlikely that pi sub y will be greater than 0. That is why, in general, that transient states are not, I mean, they don't play such an important role in this analysis. I shouldn't say, I mean, rather that probability gives 0 mass to S sub t, the set of transient states. Because intuitively also it is clear, right? We have seen that in a Markov chain having recurrent states and transient states, if the Markov chain starts in a recurrent state, then some point of time or other, it sort of gets absorbed into one of the recurrent classes, irreducible class of closed class of recurrent states. We have also seen in case of finite sample space, how to get a handle on that probability of absorption. So in any kind of limiting behavior, the role of transient states will only be minimal.
So we are claiming that pi y is equal to 0.
Not claiming. It is that is to be expected. See, this is just a motivation here. So that is why I'm saying seems very unlikely.
I mean, you are going to prove that, right?
We will see. We will see soon.
Okay.
Okay. So to further sort of elaborate on these ideas, we will look at the two examples. Rather, that example, first example. So in this example, recall that there is a unique stationary probability distribution, which is not a limiting distribution. So since P super n is P if n is odd, and it is P squared, or you can put P squared. P squared if n is even. So it follows that from the structure of P which we had seen, P, recall that all the diagonal entries are 0. Therefore, P super n ii is Pii equal to 0 for all I if n is odd. So if n is even, then you can see that these are the terms. P super n 1 is 1 minus P, P super n 2 is 1, P super n 3 is P. And for any real number, let us denote by bracket any real number xi. Bracket xi denotes the integer part of xi. I think you might have seen this notation in some other classes or subjects also. X bracket denotes integer part of x. Now using that exercise, so for example, that is G sub n at 1, 1, we have seen is that exercise says that it is summation j going from 1 to n, P super j 1, 1. And in this summation, only when n is even would play a role. So this sum is precisely this j going from 1 to, let's say, n over 2. And when it is an even j, it is all 1 minus p. So this is equal to integer part of half n times 1 minus p over n. And that converges to half of 1 minus p. In a similar way, you can see the average concerning state 2. 1 over n, j going from 1 to n, g sub n 2, 2. That goes to half. And concerning 3, you see that the average goes to half p. So getting this expression, half of 1 minus p for 1, half for 2, and half for 3, half p for 3 should immediately ring a bell. Compare these guys with pi 1, pi 2, pi 3. So pi 1, pi 2, pi 3, that we had found as the stationary probability distribution. That is, if you start with that distribution, that never changes. So that is a kind of average in the space variable. There time doesn't come into picture. Right? As one of you had also observed that it's a solution for that pi p equal to pi. Whereas these kind of objects are time averages. So we notice here that in this example, there seems to be an intricate connection between the space average and the time average. Expectation is an average, right? Yeah. And to see this connection, an object which will help us is that m sub y which we have defined. So continuing with this example, and in this case, note that T2, if you start with 2, y equal to 2, P sub 2 T2 is equal to 2. That is, at the second stage, you are back in 1 with probability 1. So P sub 2 T2 equal to 2 is equal to 1. Consequently, in this case, M2, which is the expectation of this constant random variable, is 2. And suppose y is equal to 1. Then we know that it cannot, if you start from 1, you cannot come back to 1 in odd number of steps. Therefore, P sub 1, T1 equal to 2k plus 1 is 0 for every case. And you also verify that the probability that T1 equal to 2k is this expression. This is verified. And also consequently, once you know that, please note it. Once you note that, you can find its expectation, that is 2 divided by 1 minus p. And similarly, verify that M3 is 2 over P. You will also be now seeing a relationship between pi 1, pi 2, pi 3 and M1, M2, M3. Okay. Many of you would have already guessed it, but look here that pi 1 is equal to 1 over M1. Okay, right? M2 is, rather pi 2 is 1 over M2. And for a transient state, M of y is equal to infinity. So 1 over y would be 0. All right. So I think I should stop here. This is kind of just a motivation for the result. Rather, that result, when it is stated, it might look a bit strange. That is why I just prepared you with an example that actually happens. By the way, next class is on Friday. Do any of you have any kind of issues with that? In the sense, you will be on the train or on the way to coming back to the CMI or having some other exams and things like that?
Measure theoretic probability midsem is in the afternoon, so that should be fine, I think.
I mean, this is Aniruddhan, right? Yeah.
Yes, sir.
You think you can sort of manage with that, or you want?
Yeah, it should be fine. Yeah, that should be.
Okay, I will just hold a short class, okay? Because the theorem which we are going to state, that will require measure theory. I mean, it will be. I will see. I think I may give an indication of the proof, but sort of this thing. I can just give the details, all the measure theoretic thing, but to appreciate that, one should know measure theory. So maybe I will just give the idea of the proof, and the proof later on, if one has time, for those who have done measure theory, I may do separately, or I will just later include in the notes. It is not that difficult if one knows measure theory and the strong law of large numbers. Strong law of large numbers, I will state and sort of say that that's one of the the main ingredient for the proof. So maybe Friday we will have perhaps a shorter session. Okay.
So sir, by Friday, do you want to mean the coming Friday?
Yes, coming Friday. The coming
Coming
Friday,
Friday, right? Coming Friday. Okay, fine.
Coming Friday. I mean, are you going to be on your way to CMI?
No. It's fine for me.
It's fine for you. Okay. Anybody else?
Anyway, I am not going to CMI. I am at my home only.
Okay.
So it is absolutely fine for me to have a short class or long class, anything as you wish on Friday.
Okay.
Anything as you wish on Friday. Okay,
And yeah, so we will have perhaps a shorter session on Friday, and so this thing which we have seen today might sort of make you expect that statement of the result, or rather, it will be. It will not look very strange just if you are meeting it for the first time and things like that. So this is sort of relates two things: the time average and space average.
So on Friday, what will you do? Is that any introduction to measure theoretic probability?
No. It's an introduction to measure theoretic probability. It is not at all going to be of much use. If you want to do measure theory and this, I mean, sort of have this thing, you may have to attend a course.
Okay.
Because even the very fact that why we need that strange object like sigma algebra, you will understand only if you do measure theory.
Okay.
Doing with the finite sets and even countable sets, one may always think that one can do with the power set. When you do
But
measure
okay, but
finite-
you will state strong law of large numbers, right?
strong law of large numbers, I will state. Even the statement, there is, what will involve is a strong notion of convergence, which I just will say that it's a strong notion of convergence. Okay. Why it is called strong or why it is not weak, those things I will not go into.
So, sir, will you prove the strong law of large numbers?
No,
Or simply the
sir.
statement?
For proving strong law of large numbers, you have to attend a course on measure theory,
Okay.
measure theoretic probability.
Okay. So only just the statement of the theorem.
Yes, that also for discrete random variables. Okay, so in that case, let us stop here.
Sir,
Yeah.
I think you're following Hoyle-Pot stone, right?
Pardon?
You're following the book Hoyle-Pot stone, right?
Not following. I don't follow any particular single book.
Okay.
Okay, because I feel that certain things are given better somewhere else and things like that. So Hoyle-Pot and Stone is a kind of somewhat of a guideline.
Okay. So what book would you suggest to try?
It could be several books. I don't want you to just go in search of books.
No, like for problems. I means I wanted some problems to solve to gain practice.
Solve to practice. See, this kind of problems only will be there. What I am giving in the problem set, and certain things in Hoyle-Pot and Stone. Okay.
But I think, sir, you have already uploaded problem set 3.
Yes.
Yeah, but I wanted some more problems. That's all.
See some other problems in Hoyle-Pot and Stone, or another book I have suggested is Ross's book, Sheldon Ross.
Okay.
And also in some cases, the notation might differ. You will have to untangle the notation and so on. See, in a very, very basic course, one might follow a single textbook if it is convenient. For example, last year, analysis 3, I followed something which has come out rather recently at that time, and also it was available free on the net. So I used it. Now, many of the books may not be freely available.
So, sir, is the class over for today?
Yeah, the class is over. If they say I'm following some particular book verbatim, then I need not give notes to you. No, I can just say that you read pages this to this for this class. It will make this thing also simpler.
So, is the class over?
Yeah, class over.
So, can we leave?
Yes, I'm stopping. I'm also
Okay.
ending.
Okay,
Okay.
bye, sir.
Take
Bye.
care, all of you.